Hi, I would like to talk to you about gravitational and electric fields today. So I'd like to start with an example, which may seem like it doesn't have to do with either gravity or electricity, but let's say that I explode a little small bit of metal into many very tiny pellets of metal that spread out spherically symmetrically from the center. I'm imagining that this happens in 3 dimensions. You might imagine that if I were to try and represent this in 2 dimensions on my screen, it might look a little bit like this, where like this is the path of each little bit of metal, and I've only just drawn a few little metal pellets that I've exploded my metal into here. But here's the little trajectory outward, and there's where they are. Here is something I'd like to observe. Soon, they've each traveled some distance outward. They've each traveled the same distance, if I imagine them spreading out spherically symmetrically. And so they're spread over the surface area of a sphere, like over the outside of a little ball of pellets. And so one thing that I might want to ask or remind you about is, what is the surface area of that sphere? Well, if the radius of the sphere is r, the surface area is 4 pi r squared. I wonder, is it possible that the surface area is 4/3 pi r cubed? I have trouble remembering this formula. Well, 4/3 pi r cubed would have units of meters cubed, so it couldn't be a surface area. Memorize this. Surface area of a sphere is 4 pi r squared. Well, now I'd like to consider the density of pellets in pellets per square meter, or pellets per square centimeter. You can imagine that there's this surface that the pellets are spread out, and you can imagine saying how many little pellets there are in each little patch of surface area. And so I guess, what is the density of pellets spread out over the surface area? Well, if there are n pellets spread out over a surface area of 4 pi r squared, then the density is n over 4 pi r squared. If I could put in some numbers, imagine that I exploded something into 100,000 pellets, and they've spread over a half a meter. I guess the diameter of this sphere is now 1 meter. The radius, the distance that each pellet has traveled from its original location, is half a meter. What's the density of pellets in pellets per square centimeter? Well, it turns out to be 3.2 pellets per square centimeter. So you imagine that if this were a wiffle ball, the pellets would be blasting out some holes through the wiffle ball like that, and each little square centimeter patch of wiffle ball will have 3.2 pellets if there's as many as 100,000 of them. All right. Well, let's say this. Instead of a radius of half a meter, let's consider that they're a radius of fully a meter, a diameter of 2 meters of this sphere that they're spread out over. Now what's their density? And here's what I want to pay special attention to. If this is the formula that describes their density, when we scale the radius by 2, we scale the density by what factor? 1/4. So you see how there's sort of less density of pellets when they're spread out over the larger sphere compared to when they're spread out over the smaller sphere. Same total number of pellets, but when they've moved from their small sphere that they're spread out over a little bit more in time, they're more spread out, they're spread out over a larger sphere, the density has scaled down. So there are 1/4 as many pellets per square centimeter. That's just sort of an amuse-bouche mentally for the topic that we're talking about today. Today we're talking about gravitational field and electric field, and then we'll maybe get to some similarities and distances between them during our next lecture. Well, here is an intellectual problem that's very troubling for physicists who are working on gravitation, I guess Newton in particular. I can exert a force on this cup, but only if I touch it, right? I don't have the power of the force. I can't move my cup telekinetically. I need to have contact, touching with my cup in order to apply a force on it. How is it possible that the sun could exert a force on Earth without touching it? Here is an intellectual framework that can hold the answer to that question. You might have one object creating a field in all locations in space. So this is the sun and this is Earth. The sun creates a gravitational field at all locations in space, whether or not those locations have an object there. So you might have one object create a field at all locations in space, including this object that it seems to be exerting a force on without touching. And so then, if you move the second object to a particular location with a gravitational field, the field causes the second object to experience a force. So the question was, how can one object exert a force on another object without touching it? The answer, according to a particular intellectual framework, is that the first object creates a field at different locations in space, and then an object can experience a field at its own location. A second object can experience a field at its location. So the first object causes a property of a location, a condition in a particular spot in space that is experienced by the second object. That's the intellectual framework here. We're going to have some math to say about this. Gravitational field is a property of a location, and mathematically, a gravitational field helps us figure out how much gravitational force a victim of a particular mass would experience if the victim were put at that location. It's a lot of words. If you ever want to test someone to see how fluent they are with first year physics, ask them to tell you what a field is. It's hard because it's defined in the conditional tense. A gravitational field is a property of a location that helps to tell how much force an object would experience if that object were brought to that location. This is defined in terms of its effect. So here it is. You can see that, that the gravitational field has a magnitude and a direction. It is a vector. And this equation, the gravitational force a victim placed at a certain location experiences, is equal to the gravitational field at that location times the mass of the victim. That is the definition. This statement is the definition of gravitational field. What are the units of gravitational field? Well, according to this equation, it has to be something I could multiply by kilograms to get a number of newtons. So the units of gravitational field are newtons per kilogram. You know already that that's the same as meters per second squared, but we'll have more to say about that in a bit. For example, let's say that I tell you that off-screen there's some weird shaped gravitating mass or masses, and I don't tell you any details about them, but I do tell you there's a location here, location P, right there, that purple dot, and I say, okay, a given of this problem is that at location P, the gravitational field is 2 newtons per kilogram in a direction that's a little bit up and to the left. Okay, that's a given of the problem. Here's a problem I could ask. Well, let's say I brought my 3 kilogram toy moose to that location. How much gravitational force would it experience? Well, this is the statement that's the definition of G, the definition of gravitational field. Fg equals mg, or as I wrote it above, gm. So the amount of gravitational force that a moose brought to that location would experience is 6 newtons, toy moose. And the direction of gravitational force it would experience is a little bit up and to the left. So if I bring the moose to that location and then let go, what's its gravitational acceleration? Well, it's that gravitational force divided by the mass of the moose. Notice that the masses cancel because the gravitational mass in the numerator is the same as the inertial mass in the denominator. That is quite a coincidence. And so the acceleration of the toy moose let go at that location is 2 meters per second squared. Well, let's say that instead of a toy moose brought to point P, I bring a planet to point P. What's the amount of gravitational force exerted on a planet by this weird off-screen gravitating mass if I bring the planet to location P? Well, mass times gravitational field is the gravitational force that a victim experiences. Mass times the gravitational field at that location is the force that a victim experiences when brought to that location. In this case, it looks like 14 times 10 to the 24 newtons, and it would experience a gravitational force up and to the left, the same direction as the gravitational field. And if I bring the planet there and then release it, what's its acceleration that it has? Well, same as with the moose. You divide that gravitational force by the mass, you get 2 meters per second squared. So it looks like the toy moose and the planet, when brought to this location, had very different amounts of force that this gravitational field exerted on them, but they experienced the same acceleration when you let them go because there was that cancellation in the mass. Okay, so the fact that 2 meters per second is the acceleration of both of them confirms what you probably suspected all along, as with the case on Earth, where the gravitational field is 9.8 newtons per kilogram, or 9.8 meters per second squared. At any location, the gravitational field is also the free fall acceleration at a location. Okay, the units of gravitational field are newtons per kilogram. A newton is a kilogram meters per second squared, and so yes, meters per second squared. When I told you about the toy moose and the planet, I didn't really tell you very much about those off-screen masses. I didn't tell you what their mass was, what their shape was, what their size was. I didn't need to. I told you the gravitational field at that location, and you were able to know about the forces and accelerations that a victim would experience if brought to point P. All right, you didn't actually need there to be an object at point P for me to tell you that there was a gravitational field at point P. Kind of interesting. By the way, I have used the term victim mass so far. I will also use test mass, because you can bring a mass to a particular location in space to test what the gravitational field is at that space. So test mass is a synonym. As we learn about gravitational field, this slide is about the effects of gravitational field. Next, I'm going to teach you how to figure out what the gravitational field at a location is, based on the masses that cause the gravitational field, but only in some very particular special circumstances. So, in the very particular special circumstance that a gravitational field is created by a point mass or a spherical mass, then let's see if we can figure out what the gravitational field is at that location. If there's this green mass M1 and we have a location that's a distance r from its center, let's see if we can figure out what the gravitational field is there. Well, if we put a victim mass there, a test mass, the victim will feel a gravitational force given by Newton's law of universal gravitation. The gravitational force on the victim is equal to big G times the mass of the planet divided by that distance r squared times the mass of the victim. But in the previous slide, we just said that the gravitational force at a location, the gravitational force on a victim at a location is equal to the gravitational field at the location times the mass of the victim. So it looks like we've just proven that the gravitational field at that location is big G times the mass of the planet creating the gravitational field divided by that distance r squared. Note, and this is absolutely key, you don't have to have a mass at this location to have a gravitational field at that location, a condition of that point in space. And you certainly don't need the mass of a victim in order to calculate in newtons per kilogram how strong the gravitational field is. Alrighty. Here's another example. Let's say that the object is Earth, and we're interested in calculating the gravitational field right there. Well, it should be equal to big G times the mass of Earth times the square of Earth's radius. And yep, there's the value of big G, 6.67 times 10 to the negative 11th. There's the mass of Earth. There's the radius of Earth, squaring it. Anyone know what this is going to turn out to be when we put it in our calculator? Boom, our old friend 9.8 newtons per kilogram, the local gravitational field at the surface of Earth, aka 9.8 meters per second squared. Cool. Well, let's say that I was able to get a person a radius of Earth's radius above the surface of the Earth, a height above the surface of the Earth equal to Earth's radius. And if I were to let this person go, what would this person's acceleration be? Well, let's consider the gravitational field at that location. We've considered a location that's twice as far from Earth's center. So according to this formula for the gravitational field, for the acceleration due to gravity, when we double the distance from Earth's center, we should quarter the local gravitational field strength. We should quarter the acceleration due to gravity. So a person or a toy moose or whatever, released at that location would fall towards Earth with an acceleration of about 2.5 meters per second squared, a quarter what there is at Earth's surface. Cool. Now I'd like to talk to you about electric field. Electric field, very similar to gravitational field. It is a property of a location in space, not a property of an object, not a property of a distribution of charges or anything like that. It's a property of a location, a spot in space. And it helps us determine the amount of electric force a victim of a particular charge would experience if a victim were brought to that location. So, I guess here I showed the weird objects on screen. So here are some charged objects. This is some red positive charges and a blue negative charge. Here's the definition of electric field. The amount of electric force that a victim would experience if brought to location P is equal to the electric field at location P times the charge of the victim. And this is a true vector equation. You can see that the direction of the electric field is the same as the direction of electric force that a positive charge would experience. We'll say a little bit more about that in a bit. What are the units of electric field? Well, newtons per coulomb. How many newtons of force per coulomb of charge? And since a coulomb is such a big charge, you'd imagine that there would be a huge amount of force that a coulomb of charge would experience. So most of our lab electric fields would be quite large. One would be a very small electric field. 1 newton per coulomb would be very small. Okay, so if I tell you that at a particular location P, there's an electric field of 15 newtons per coulomb, a little bit down and to the left, then how much electric force would a 2 nanocoulomb test charge feel if put there? Why, 30 times 10 to the minus 9 newtons, 30 nanonewtons. And what direction would this positive test charge experience a force? Well, according to this equation, the same direction as the electric field. This positive charge times this direction gives an electric force in the same direction. If we had a negative charge, what electric force would it experience if brought to that location with a given electric field? It would have the same magnitude of electric force but opposite direction. If you consider that we took the vector 2, if we took the vector electric field 15 newtons per coulomb and multiplied it by, and the direction was down and to the left, and multiplied it by negative 2 nanocoulombs, then the negative would sort of flip the direction of the electric field vector. The force on a negative test charge points opposite the electric field vector. If I bring a test charge to a particular location and let go, like I did with the gravitational force, well, I don't have anything cool to say about that, like I did with the gravitational force, because there was an mg in the numerator before, but now there's a qe, and so the m doesn't cancel. I don't have anything to say about the acceleration due to the electric force. It's not the electric field is not an acceleration as gravitational field is. Okay. So now that we've talked about the effects of electric field, let's talk about the generation, the creation of an electric field. And let's talk about it in a particular case of a point charge. So let's say a given of this problem is that we have a charge Q right there, and I'm interested in calculating the electric field at that location, that spot in space right there. Again, I'm not saying there's a charge there, a victim, a test charge, to experience any kind of electric force. But even in the absence of a charge there, I can still talk about the electric field at that location. Okay, well, if Q, the amount of charge creating the field, is a given of the problem, and so is this distance r that point P is displaced from the charge creating electric field, let me talk about the magnitude of the electric field created, and then I'll talk about the direction of the electric field created later. If I put a positive test charge at point P there, then, and this is going to be just like we did with the gravitational force, the amount of force on that positive test charge is kq, that q, times the test charge divided by the distance r squared. And there's just the, I guess, the associative property of equality. I've just rearranged the equation. But we just defined the magnitude of an electric field to, with this equation. The amount of electric force that a test charge would experience at a location is equal to the magnitude of electric field at that location times the amount of the test charge. And so, yeah, the amount of electric field at a location is equal to k times the amount of charge creating the electric field divided by the square of the distance between the charge creating the field and the location that you're talking about. Usually I will drop my magnitude signs. This is an equation, again, that only describes the electric field from a point charge. Now let's separately talk about the direction of electric field. Let me get this out of the way so I can just focus on this business to the left. If there's a positive charge here generating an electric field at point P, what direction is the electric field at point P? Well, the way you do this, the way you think about it, is imagine a positive test charge at point P. What direction would a positive test charge experience an electric force? Away from that charge Q. So the direction of the electric field is away from that positive charge. If instead we have this negative charge there, we still imagine putting a positive test charge at this location when we ask the question, what direction is the electric field at this location? And if there were a positive charge there, it would be attracted to that negative charge. So I know that the electric field at this location P is towards that negative Q charge. Let me just show you this. So I think if I do this, the direction of the electric field in this case is that away, and in this case it's that away. I can do this all in one vector equation if you want. You definitely don't have to do this, but the vector electric field as a function of vector displacement from a point charge is equal to k times the magnitude of the point charge divided by the distance between those two squared times r hat, where r is a unit vector from the point charge towards the location P. If this is intriguing to you, then great. Let me talk about some similarities and differences between the gravitational force and the electric force. You can see just on the face, their equations seem quite similar. We're talking about the gravitational force between two objects that we can treat as point objects. There's a sort of a constant of nature times the product of the masses divided by their separation squared. And if we have two objects that we can treat as point charges, the electric force between them is equal to Coulomb's constant, a constant of nature, times the product of their charges divided by the square of the distance between them. So there's some pretty obvious similarities. One is this over r squared dependence. And you might wonder, why would both the electric force and the gravitational force have a 1 over r squared dependence? They get weaker as two objects are separated more and more, and when the distance between objects is doubled, the force scales by a quarter in both cases. Why is that? Well, remember our amuse-bouche? Remember, amuse-bouche is like an appetizer. It's French for mouth amuser. It's something that you have at like a fancy restaurant before you even have appetizers. Amuse-bouche. That's the word of the day. Remember this? That when you explode something and stuff radiates outward in all directions, the density of that stuff falls off as 1 over r squared? Well, this is relevant to the 1 over r squared term in both of these force laws. You might imagine, is there actually a set of particles emanating from a charge whose density falls off as 1 over r squared, and this controls the 1 over r squared dependence of the electric field? Yes, the idea is that a charge emanates particles that sort of announce that it is a charge. And then depending on the density of those particles at a particular location in space, a charge brought there would respond to the original charge based on the density of those emanated particles. And that these particles are spreading out over spheres that get bigger and bigger. What is the name of the particle that emanates from charges and whose density falls off as 1 over r squared in the case of the electric force? Those emanating particles are called photons. Photons of light or of cell phone transmission. Photons are the elementary particle, the boson, that mediates the electric force. And so you might ask, what is the particle that spreads out from masses to sort of announce, hey, I'm a mass, respond accordingly, and which falls off in density as 1 over r squared? Well, gravitons have been theorized but not yet discovered. So maybe you will go on to confirm the existence of gravitons that account for the 1 over r squared dependence of the gravitational force law. There are some differences between gravitational field and electric field. For one, the electric force is much stronger. If you have 2 electrons with the charge of an electron, an elementary charge, and the mass of an electron, an elementary mass, the electric force between them is many orders of magnitude stronger than the gravitational force between them. Like, what is that? 43 orders of magnitude stronger electric force than gravitational force between 2 electrons. Another difference between the electric and the gravitational forces is that there is positive and negative charge, but there is not positive and negative mass. There seems to only be positive mass. Over long ranges and time periods, mass aggregates as planets, stars, solar systems, galaxies. And only very, very large clumping togethers of mass exerts appreciable gravitational forces. Meanwhile, positive and negative charges, you can have local concentrations of positive charge, local concentrations of negative charge. But over long ranges and time periods, the positive and negative charges tend to mix such that each region of space contains about the same amount of positive charge as negative charge. That's true of, say, your body. You are not a local concentration of positive or negative charge. And so you don't exert very strong electric forces on your neighbor because even though the electric force is very strong, you have about as much positive charge as negative charge.